Right?
No, but they're
It's
not allowed
incredible,
to,
but it's
because
possible.
I mean, you would say, okay, the expansion reaches the fractional area change. That thing is always negative. So you've already reached zero area. From that, you can only go to negative area. That is a statement that's given made by the fractional area.
Okay.
It is not the antibody crossing that is. That
Everyone settled down? Shall we start? We're very pleased to have Laurent Loinard today from the National Autonomous University of Mexico. He's going to tell us about VLBI and black hole astrometry. And after the colloquium, whoever wants to come for dinner, I'll have 8 spots. And whoever wants to come to dinner, you can just come and tell me. I'll be here. Okay. So take it away.
All right, thanks. All right, so hi everybody, thanks for coming. For those of you who are also in the ngEHT program project and were there in my small talk a couple of weeks ago, don't worry, it's not just a repeat of what I said today. But it is very strongly related. So I'm going to be telling you about VLBI and black hole astrometry. And I should start my talk by saying that I really come from the VLBI community and from the astrometry VLBI community. And one of my main goals being here this year is to actually see exactly what we can do for black hole studies using VLBI astrometry and what we need. Also, in the sense of what the potential is for black hole astrometry. But also what needs to be done in practical terms to make that happen with the next generation of VLBI instruments. So I assume that you're not actually allowed to set foot in this building if you don't know anything about VLBI. But in case you snuck through the back door, I'm going to say a few things. So VLBI, of course, means very long baseline interferometry. It's a radio technique that consists in observing your favorite target with an array of telescopes distributed over hundreds or thousands of kilometers. So for instance, here, this is one of the recent ngEHT experiments, Event Horizon Telescope experiments, combining half a dozen telescopes across the American continent, plus Europe, Hawaii, etc. And in this kind of experiments, each telescope does not act as an imaging machine, it acts as an electric field sensor. So the incident wave, electromagnetic wave from your target arrives to the telescope, and what the telescope does is that it senses the electric field of that incident electromagnetic wave, digitizes it, and so it produces a time series essentially of the electric field values that it records on computer disks. And then this is recorded together with a very precise time standard from an atomic clock. And these tapes where everything was recorded and they are then sent to a centralized computing facility. There's one here in Haystack, there's another one in Bonn. And what the dedicated computer, supercomputer does is that it calculates these mutual coherence function of the electric field. Actually, it does a digitized version of this because this is a time series. But essentially, what it does is calculate this function, the mutual coherence function of the electric field. Where here 1 and 2 are 2 telescopes. So it does that for each pair of telescope in your array. And this function here is a function of tau, where tau is the fundamental quantity in interferometry. It's the delay between the arrival time of the electric wave or the electromagnetic wave on one antenna and the other one. So this is basically this distance. So this function, the autocorrelation function, the self cross correlation function, is a function of this parameter tau. Okay. And you can see already sort of speaking a bit in advance here that tau, of course, depends on theta. In other words, it depends on the position of your target on the sky. And so tau, we'll see later, also encodes the astrometry information. It encodes where the source is on the sky. And there's a very general theorem of Fourier optics or statistical optics called the Van Sittert-Zernike theorem. I should have written this here, which states that under fairly general conditions, this quantity, the mutual coherence function of the electric field, is in fact the Fourier transform of the sky brightness. In other words, it's the Fourier transform of the image, right? And here I've introduced coordinates. The previous one was sort of coordinate free. Here the coordinates L and M are the coordinates on the sky, measured from the center of the field where you're pointing your telescopes. So these are angular coordinates. And U and V are the coordinates of the baseline. In other words, it's the separation between the antenna projected onto perpendicular axes, one in the east-west and the other one in the north-south direction. So all this to say that when you do VLBI observations, what you're measuring is this function, or which we can write in terms of U and V. So you're measuring components of the UV transform of your image, right? And if you want to reconstruct your image, you need to take the inverse Fourier transform to get your image. All this is written in the Bible that Jim Moran here has written. So of course, this technique has been used. One of the characteristics of this technique is that you can, in principle, make the separation between your antennas or your telescopes as large as you want. And so you can get an extremely high angular resolution because the angular resolution of this telescope, like any other optical instrument, goes as lambda over d. I don't know where. Can I disappear?
Yeah.
Okay. So the angular resolution of the telescope goes as lambda over b, where lambda is the wavelength you're observing at, and b is the separation, the maximum separation between your telescopes. So if you make b very large, you can make your angular resolution extremely high. I should say, though, that one of the limitations of this technique, of course, or maybe the main limitation of this technique, is that you have to be able to do that operation. You have to be able to sense and digitize the electric field at each of your telescopes. And at the moment, we only know how to do that in the radio up to maybe the very far infrared, but we can't do that in the optical or X-rays or gamma rays, you know. And so that means that although, of course, doing it at higher frequencies, shorter wavelengths, would give you even higher angular resolution, we can't do that because we don't have the technology to digitize very high frequency signals. So in any case, even at radio wavelengths, this is actually the technique that provides the highest angular resolution in all of astronomy. And this was beautifully demonstrated, of course, with the Event Horizon Telescope, which uses the technique and which produced these beautiful images of M87 and more recently, Sagittarius.
What is the problem with the high frequency?
That in order for you to apply that technique, you need to be able to calculate this function. And to calculate this function, you need to be able to digitize the electric field at a very high cadence compared to the frequency of the electric field. And so technologically, we don't have the apparatus to digitize, say, optical or UV photons or electromagnetic waves at that sufficient rate. So it's a technological thing. All right. So one aspect of this that I want to emphasize is the fact that, of course, again, this step here is crucial. And this step, what it does is it really senses the electric field at very high cadence so that we can recover both the amplitude and the phase of the electric field. In other words, this type of detection that is done at each of the telescopes is coherent. It preserves the phase information. And this, of course, is extremely important because when you calculate this function here, the tau that appears, I should go back here probably. The tau that appears here, if you assume that the electric field goes as exponential I omega t, then it appears as an I omega tau term. In other words, it appears as a phase term. So you need to be able to preserve the phase to be able to calculate these quantities. So the coherent aspect of the detection is crucial for this to work, and as we will see later, also for astrometry to work. All right, so this is my sort of 101 VLBI tutorial. Now, 101 astrometry. Well, astrometry, of course, is the study of the position of objects. Wikipedia says it beautifully. It's a branch of astronomy that involves precise measurement of the position and movement of stars or other celestial bodies. And of course, we know that this is both the most ancient part of astronomy, you know, the Greek astronomers, if we can call them that, already did astrometry, right, and did beautiful things with astrometry. But it's also currently at the forefront of astronomical research because we have this incredible instrument, the Gaia satellite and other VLBI instruments that I'm going to talk about that produce really exquisite astrometric results that really touch upon a lot of essentially all of astrophysics. So one of the things that I want to say about this is it's kind of, if you do single epoch astrometry, in other words, if you just measure the position of sources on the sky, what you can do is basically construct a reference frame based on whatever sample of objects you're looking at. And this is what's being used for defining the fundamental reference frames that we use in astronomy and in astrophysics. And I think that there's interesting aspects about this regarding fundamental physics, like the Mach principle that states in different ways that it's the distribution of matter in the entire space that matters. So knowing where this space is, how this space is distributed, I think has direct relevance to this. But maybe more important, or at least what we tend to do more often as astrometrists is, if you can measure very accurately the position of some objects, and you repeat the observations, you can also see how they move. And so this is the core of astrometric research, to measure true and apparent motion of our favorite objects. So the reason this is so fundamental is that, of course, one of the most important apparent motions that objects in the sky can undergo is their trigonometric parallaxes. So this is due to the motion of the Earth around the sun, which makes it such that if you look at the same object, here the red star, for instance, in the direction of some known constellation, it doesn't have to be a known constellation, it's just a reference, and you observe it at a certain time in the orbit, you're going to see the star in a certain position, in this case, close to this star here, and you observe it again 6 months later, and you're going to see it in a slightly different position because just your perspective has changed, right? So it's not a true motion. The star in this model has not actually moved. It's just that your position has moved, so you're looking at it from two slightly different perspectives. And it turns out if you can measure that change of position, then you can know the distance to the object immediately. And so if you can measure that change of position very accurately, you can know the position very accurately. Of course, stars also move relative to the sun. So combined with this parallax motion, there's also a proper motion, as it's called, the true motion of the star relative to the sun. And so you see this kind of helical motion on the sky. Now, one important thing here, it's often said that this step, the parallax step, is the first ladder in the distance scale in the universe. That's not really true. The first ladder is actually the dynamics of the solar motion, because if you want to translate the parallax angle into a distance, you need to know exactly the orbit of the Earth around the sun. So the dynamics of the solar system is actually the most fundamental ladder in this system. So historically, this has led to what is called the cosmic distance ladder, where you measure, to know the distance to your favorite object or sample of objects, you need to go through different, calibration steps, which, as I said, start with solar system study, so typically laser ranging in the solar system, parallax to nearby stars, etc. And this is we've had actually a bunch of talks recently about this regarding the Hubble constant tension, where this kind of plot has been shown. This is a plot of basically the geometric versus the luminosity distance of a bunch of objects. And the slope of this diagram is the Hubble constant, or the inverse of the Hubble constant. And in order to really measure the Hubble constant well, we need to get in what's called a Hubble float, so fairly distant objects where the random peculiar motion are kind of averaged out. So, and also if we want to see how the Hubble constant changes, we need to go to fairly high distances, fairly high budgets. So the most common probes to do that are type 1a supernovae, which are fairly distant, but to calibrate the type 1a supernovae, you need previous steps that go all the way down to calibrating the scale with parallaxes based on Gaia. So this is, the astrometry is kind of the founding stone of a lot of astrophysics, or most of astrophysics. So now, how does one do astrometry with the VLBI array? So here, the fundamental quantity again is this delay, this time delay, because this time delay depends on the direction. If you write this b dot s, b is the separation between the telescopes, s is the direction you're looking at. The angle between the two is this theta angle on the figure, which basically encodes where the source is on the sky. So what you want, if you want to do astrometry with VLBI, you need to measure theta. And the way you measure theta is you measure tau. So this is the fundamental quantity. And how well you can measure this value depends on how well you can calibrate your observations, both the instrumental part and the atmospheric part of the signal propagation. And at the moment, the limit that we have is that we can calibrate tau to a couple of nanoseconds, basically, which is quite amazing if you think about it. And it means that we can measure the path, this c tau distance, to an accuracy of about 2 centimeters. Okay? Well, it's not nanoseconds, I said it wrong. 2 centimeters is the error on c tau, okay, that we can typically obtain. So if you use that formula up there and you calculate, you differentiate it so that from the error on tau, you can deduce the error on theta, you'll see that typically this corresponds to an accuracy of about 0.5 milliarc seconds. So this is kind of the accuracy that you can get natively from VLBI observation, about a fraction of a milliarc second. Okay. So now this is done. So let me just very quickly make a small aside here. Of course, the reason black holes are important, there are many reasons why black holes are important, but astrometry, radio observations are really very strongly geared toward black hole, because if you take an image of the sky in the radio, so this is, for instance, an image obtained, I think, at 8 gigahertz frequency from a single dish, and as you can see, there's a bunch of objects here. Almost every single object you see is either a black hole or at least a close cousin of a black hole. So a lot of these things, the extended stuff, roundish things, are supernovae remnants that probably have black holes at the center. The sort of elongated things like this are jets coming from radio galaxies that have black holes at their center. And all these little dots that look like stars, they are not really stars, they are mostly quasi-stars, they are quasars, they are distant black holes in the universe. And I'm sure in this image there are no stars at all, actually, maybe one. We'd have to check. But really, with the sky that we see in the radio is very different. It looks kind of the same, but it's very different. It's not the same object that we are seeing in the Earth. Most of what we are seeing are actually black holes, and maybe neutron stars a few. So astrometry with VLBI is almost doomed to be astrometry of black holes, because that's what we see mostly in the radio. So now going back to this astrometry thing, so these kind of observations that yield 0.5 milliarc second accuracy is what's used to do all sky global astrometry. So this has been done repeatedly over the years, and the goal here has been to realize a reference frame, as inertial as possible reference frame that we can use for any purpose we might want to use. And so this has finally led to what is called the International Celestial Reference Frame, which is a reference frame based on observations of distant radio quasars, mostly. This is the entire sky that we are looking at in this image. And each point is one radio source. There's about 4,500 radio sources in this image. And the color code refers to how accurate the positions are measured. And so you can see that a lot of the quasars have positions between 0, and it is clipped. In fact, some of the very dark red ones have accuracies maybe up to 10 milliarcseconds. But most of the targets in this image have accuracies, positional accuracies between 0 and 1 milliarcsecond, which is what you expect given typical accuracy of a half milliarsecond. And you can see here that also that the situation is much better in the north than in the south, and that's because historically most of the radio VLBI arrays were in the north. And another thing that I want to show very quickly, Dom, of course, knows that better than me, is that if you go to higher frequencies, so the previous image was the ICRF based on 8.4 gigahertz observations, so about 4 centimeter observations. So sort of the middle of the centimeter band. If you go to higher frequencies, this is K band, so this is 22 gigahertz where the water measures are located. The density of quasars is much lower. So, we need, one of the things we need is to densify the number of quasars with known position at higher frequencies. The VLBI, the ngEHT, as you know, works at 230 gigahertz, so much, much, much higher than this, 10 times higher. And I don't have a plot of the density of good quasars at 230, but if I had one, it could be very, very boring. It would be very few points. So, yeah.
How does the distance distribution of the reference set go? I mean, are they the 300 defining sources? Are they mostly far in?
So they're all far away. They're all not at Z of 10, but they're all kind of cosmological distances. But what does define the ones that are used as the defining sources of the ICRF, the 300 subset here, is not how far they are, it's how compact they are, which might be indirectly related. But so in this sample, you have all kinds of, these are images of some of these sources. And they've been classified into different categories. The best ones are these ones here. They are very compact, very well defined. They don't have any internal structure at the resolution that they are observed. And they don't change with time. So they are very good anchor points for this kind of work. Whereas this is the second category. The third category can have very long jets, which are, in addition, they can be variable, so they are not as good calibrators in this sense. So out of these, what these guys did was to make images of these 4,500 sources, and then from these, they selected the 300 that were the most compact and the most featureless and the most time constant that they could find. I don't think they worried about what distance they were. They're all far enough that they don't move. And well, with one caveat that I'm going to show. And this is what defines the ICRF. So if you want to do astrometry, these are the guys that you use as calibrator. Right? This is kind of a grid on the sky that you have, relative to which you can measure positions very accurately. And as I was saying earlier, if you want to do astrometry at 22 gigahertz, then you're in more trouble. You have less anchor points that you can use. And if you want to do that at 86 or at 230 gigahertz, it gets worse.
How many of those 300 anchor points are here? In other words,
on this one, I don't know.
Maybe you have enough here.
Maybe you do. Well, maybe you have enough to I don't. The answer is I don't know. But even if you do have enough to define an ICRF at K bands, you know, if you pick your favorite target and it's here, you're still in trouble, right? Because you don't have a good calibrator nearby that you can use as a phase reference. So it's not just how many can be used to define. That's actually why they have 4,500, right? You do need a number of very good ones to define your ICRF, but then you also need a dense grid that you can use as phase references for VLBI observation. All right, so okay, so if you care about reference frames, this is important, and you should care about reference frame, because if you don't have reference frame, you can't do astrometry. But let's talk about some what I think are cool applications of these kinds of things. So we've all heard about stellar aberration, right? So stellar aberration is this effect where if you're looking at a star or at any target on the sky, any object on the sky, from a lab that's moving relative to that star, then the motion that you have relative to the star is going to make you see the star in a position that's different, in a direction that's different from the one it's actually located. So it's like when you're running, imagine it's raining, there's no wind, so the rain is falling vertically. If you're running relative to this, you're going to be hit in the face because you're seeing the rays that are actually vertical incline. Okay, so the formula is this, and notice that it only depends on the velocity of that observatory that you're sitting on, and it depends, of course, on the angle. So what this produces is that if you have an observer that's moving at constant speed relative to the sky, then that observer is going to see all the stars in slightly different directions from where they really are. Okay, it's a shift. It's a positional shift. It's a shift that depends on where they are. So there's a pattern on the sky of displacements. The shift is different if you're for the stars that are exactly in the direction you're moving and the ones that are perpendicular to it. So it's a shift that's position dependent, but it's just a shift. Okay? On the other hand, if you're sitting on an accelerated frame, then because you have an acceleration, you don't have a constant speed. And so this same effect produces a position-dependent velocity pattern on the sky, a pattern of proper motion, in other words, right? So this is what's called the secular aberration. I know there's some different people use different terms for this, but this is, I think this is the most accepted term, secular aberration. And it turns out, of course, we are on an accelerated frame. So of course, we're going around the sun, but that we know well enough that we can correct for this. In fact, this effect was detected since we are in a center where history of science is also studied. It might be worth mentioning that this effect was actually detected for the first time in the early 18th century by a British fellow called Bradley, who was actually trying to detect parallaxes. You know, it was still short enough after the introduction of the Copernican system that people were trying to prove the Copernican system by showing that there was a parallax due to the motion of the Earth around the sun. So that's what he was trying to see. He was actually looking, I read this yesterday, that's an interesting story. He was looking at a star that from London is almost exactly overhead through his chimney. And, I kid you not. And he was, every night he was looking at it, and he found that indeed the star was going in this motion throughout the year, except there were two problems. One is the motion was fairly large. It was like 40 seconds about, which was larger than people anticipated. But more importantly, it was going the wrong way around. It was not. If you look at the parallax, and you'll see that they both provoke an elliptical path on the sky, but they are not going in the right direction. And so he correctly
the wrong way around because it's in England.
Sorry. That's right. They're going on the wrong side of the road. That's how it was detected. And the parallax, the true parallax, the parallax was actually detected almost exactly a century later. So in any case, what I'm referring to is not the motion of the Earth around the sun. What I'm referring to is the motion of the sun around the galactic center, which is more or less a circular motion around the galactic center, and which provokes an acceleration, a normal acceleration. So this was actually detected, and I think this is quite cool, really. So this is from the same paper of the ICRF that I showed earlier. And this is the pattern that is seen of apparent, so it's an apparent proper motion. It's not a true proper motion. The quasars are also moving, of course, but this is not what is seen here. This is what they've done is exactly how, I don't know, but they've defined cells in this plane. This is coordinates, right? On the sky, right? Ascension, declination. They've defined cells here, and in each cell, they've averaged the proper motion of the quasar, that cell, to produce these arrows. And these arrows show the motion in milliseconds or microseconds of Earth per year, apparently seen for these quasars. And you can see there's clearly a very well-defined pattern where all the arrows are coming out from here and all the arrows are entering here. This here is the galactic center. So this is exactly where the acceleration is pointing, which is what you would expect. And you can calculate, these are the equations that you expect for these proper motions. So there's a projection term, the pattern is position dependent. And then there's the amplitude of the motion, AG, which can be calculated by this equation up there. And I actually forgot which is which, but yeah, I remember. So the fit to these positions give an AG of 5.8 microarcseconds per year. And if you take the most recent values for the galactic parameters for V0 and R0, the rotation of the sun around the galactic center and the distance from the sun to the galactic center, you expect about 6.1. So there might be a little tension, but I wouldn't put too much emphasis on this at the moment. Right? This is fairly recent. The first measurements of these things were made by Titov and collaborators about 10 years ago. So I think that's pretty cool, personally. All right. So with this, I finish sort of the first part of the talk, which was kind of the global aspect. You just measure global astrometry. You look at all the sources on the sky. But you can actually do something that's also very interesting, which is local astrometry. So once you have, in other words, instead of measuring, you have targets over the entire sky, and what you're trying to do is measure the distance, the angular distance between these targets. You can take a little piece of the sky and worry about the distance between the targets in that little piece of the sky. So instead of doing global, absolute astrometry, you do small field relative astrometry. Okay? So what I described earlier falls in the first category, the whole sky global astrometry. That's the way the ICRF is defined, and that's also the way the Gaia satellite works. But for VLBI, an important subfield is the local aspect of things, where you measure positions for stars that are objects that are maybe a few degrees apart on the sky, rather than 360 degrees apart. And for VLBI, this is done using a specific technique called phase referencing. So how that works is you basically use, that's what I was saying earlier, you use one of these guys as your anchor point on the sky, and you measure. So one or more of these guys are your calibrators, and then you measure the position of your target, your favorite target, relative to these guys. So one is the minimum. If you use a few, that's better. And it turns out that for calibration terms that are only antenna dependent, that only depend on each antenna. So either, the instrumentation of the antenna or the sky above the antenna, only the sky above the antenna. The uncertainty that you get is the same uncertainty that you had before, multiplied by the separation between your reference, your calibrator, and your favorite target in radians. And since, if your separation is, say, 1 degree, that's a very small number in radians, but much smaller than 1. So you multiply this 0.5 milliardsecond uncertainty that you had before by a number that's much smaller than 1. And so you get a much higher accuracy. You get an uncertainty that drops to about 10 microarcseconds, which is extremely high accuracy. It's at least as good and probably better than the Gaia satellite. So this is just like VLBI provides the highest angular resolution images you can get. It also provides the highest relative astrometry that you can get. So there's a whole bunch of things you can do once you have that kind of accuracy. One which has been known for a long time is the so-called core shift. So if you have a quasar that emits a jet, opacity effects within the jet are such that make images of the same object at different frequencies, the position of the core changes with frequency. And so this is our favorite AGN M87, studied by Ada and collaborators at different frequencies from 1 to 40 something gigahertz. And this is the position, this is the offset in position as a function of frequency. So you can see that the position changes as a function of frequency. And as you go to higher and higher frequency, it tends towards a certain specific value, which is where we think the black hole is actually located. If you, there's a bunch of possibilities to explain this. The most likely is, as I said, the opacity of the emission process itself. And if that's the case, then you expect this curve to be 1 over the frequency. And when they fit it, they get 1 over the frequency to the 0.94, which is close enough. But what this means is in terms of so this is an interesting effect by itself, but it also has an important implication for astrometry, because what it means is even if you have the same calibrators that you're using, so you have the same points of the sky that you're using as calibrators, if you do it at 2 different frequencies, they won't necessarily be at the same position. So this is something that you have to worry about. Going or continuing with our favorite target, Sagittarius Star. So Sagittarius Star is the black hole at the center of the Milky Way, and it's a radio source, which has been imaged also with the ngEHT, but at lower frequency, it's been observed astrometrically in the last 20 or 30 years now. And that allows you to see its proper motion, its actual motion on the plane of the sky. So these are the different measurements in red here that have been made. The blue line is the galactic plane. So you can see that it's moving more or less along the galactic plane, not quite. So you could say, so what's happening? Why is it moving relative to the galactic plane? Well, it's not really that it's moving relative to the galactic plane, it's that we are moving relative to the galactic center. And so we see it apparently moving towards the galactic plane. And in fact, if you correct for the motion of the sun around the galactic center, you'll find that the residual motion is only less than 1 kilometer a second in both vertical and horizontal direction. In other words, thankfully, the galactic center is also the dynamic center of the Milky Way, which is good to know. We could have suspected this, but it's good to have a confirmation. The accuracy is good enough that you can even do extragalactic motion. So this was a paper already 20 years ago, based on fairly strong water masers in this galaxy M83 of two star-forming regions here that were, the accuracy of the measurements was good enough that you could actually see the rotation of M33, which historically is interesting because before it was accepted that spiral nebulae were actually external galaxies to our own Milky Way. People tried to measure rotation of these nebulae to see if they rotated at all. If they rotated, that meant they had to be within our own galaxy, because otherwise they would have to rotate faster than the speed of light. And this Dutch astronomer von Manen, in fact, reported a bunch of experiments where he pretended to have, or he claimed to have detected the rotation of several spiral galaxies, including M36. So it took about 100 years to actually get the measurement.
Sorry, but those numbers are not right.
Sorry?
On the right one?
No. This was some artifact that I don't know what the source of the error exactly was, but this was not right.
It looks really.
It looks good.
Well, I'm thinking like, wow, you really.
The two images were clearly rotated like this.
That's all just wrong.
Whole thinking.
That's all wrong, yeah. There's a whole bunch of papers in Object. This is from Object.
Yeah, what are they looking at? What is that of?
Stars, just stars, I guess.
That must have been such a willful This
know.
representation.
I know. Yeah, because it's the pattern, there's really a pattern. You know, I should have looked in more detail about.
I'm sure it was just the placeholder.
Yeah, but you usually don't do that arbitrarily, right? You take, standard stars that you think are fixed, and then that's how you align your plates.
Yes, this is like when you drop your golf ball and you're like this.
Yeah, exactly, yeah. Come on. You should cut him a break. It's 1923. Come on.
Yeah, exactly.
I'll tell them in person.
Yeah, please.
You had a question or?
No, so this is a nebula that's rotating or a galaxy? I didn't catch
So
that.
this is a galaxy. This is a galaxy,
Okay.
and what they looked at were, but this is real. This is an actual measurement that
Oh,
we trust.
okay. Okay.
This is a VLBI measurement based on water measures in that galaxy. So some star forming regions where massive stars are born, have this water measure that can be used to do astrometry very accurately. And they did astrometry of these two guys and found the rotation. But at a level that's at least 10,000 times smaller than what was claimed here.
They're training.
This trend doesn't continue for another 100 years.
Yeah.
Yeah, in 100 years, we'll have this picture,
So
but true.
to detect that rotation, how long did they have to observe it?
It's only a few years, actually. It's not a long time.
Very fast.
It's
Is that
really
because
cool.
they have like micro-second?
They have sort of 10 micro-second accuracy on individual epochs.
Oh.
So you calculate, the proper motion, of course, the advantage is it's a cumulative effect, right? So if you, as you said, if you don't wait long enough,
So it's a
It's sort of-
tiny rotation, but you have great accuracy.
you have extremely great accuracy. So you can see, in other words, you can see, this is typically a few hundred kilometers per second, the rotation speed. So you can see few hundred kilometers a second at 1 megaparsec. Yeah. So I should give the screen to Dom here, but this can also be used to measure the Hubble constant. So the way this is done is by looking again at galaxies that have water measures, but in this case, not associated with star forming regions, associated with the nuclear region of these galaxies themselves. And so these water measures trace disks, circumnuclear disks in these galaxies that you can observe at different epochs, and you can see how they rotate. You combine that with observations of the radial velocities, and you can measure the distance, very accurately, the distance to these objects. And since you also have the velocity, you can get the Hubble constant. And so this is a plot that I forgot her name, sorry. Di Valentina showed a few weeks ago. They are now.
It's not 1921.
2020.
Sorry. A few weeks ago. 2001. 2021. Sorry about it. So these are many different measurements of the Hubble constant. The one above the line here are based on the cosmic microwave background, and they tend to give a low value around 68, whereas the ones at the bottom are local measurements of the Hubble constant, which tend to give values around 72. And it includes this value from Dom's paper somewhere. And so, and Dom, this is only based on, as you can see, a few water measurements, but it's also, it's very accurate. You get very accurate. All right, so this is another thing where VLBI astrometry can contribute. As I'm going to go very quickly because I really want to get to the end. You can use, as I said earlier, you can use this technique to measure parallaxes and therefore distances very accurately. This has been done in many objects. You can do that to, for instance, compare with the Gaia results, and you find that there's some tension with the Gaia results. But one of I'm going to show you a few of the coolest kind of results of this. One is how you can use, again, water measures now in our own Milky Way, associated with star forming regions in our own Milky Way, to trace out the structure of our Milky Way and the size and dynamics of the Milky Way. So in particular, you can see that each of these points is one of these star-forming regions. They are lined along structures that we call spiral arms, and they define these spiral arms very accurately. And from the astrometry, you can get the fundamental parameters of the Milky Way, the distance from the sun to the center of the Milky Way, and the velocity of rotation, which are the values that you needed earlier to calculate the secular aberration. And you can also very nicely define the rotation curve of the Milky Way and therefore the mass of the Milky Way. So these are, I think, very important results. You can look at black holes in our own Milky Way, stellar mass black holes. So for instance, there's this very nice series of papers by Miller Jones and collaborators that looked at Cygnus X1, one of the best known X-ray binaries in the Milky Way. And they can measure the distance very accurately and therefore can put very strong constraints also on the mass of these stellar mass black holes. And just very quickly, one of my own interests is because the Gaia satellite and VLBI are the only two techniques that give you sort of the level of 10 microarcsecond accuracy. You can use one to check the other and vice versa. And so in this paper, Leonard Lindgren, one of the Gaia gurus, compared the astrometry of Gaia and VLBI and found that there's some tension between the two in terms of defining a reference frame. So this is something that I actually intend to keep working on. All right, but in the last 5-10 minutes, what I wanted to focus on is, so everything I showed you is based on existing VLBI instruments. There are, I think, very cool results, but we can expect with the next generation of VLBI telescopes, I think we can expect even cooler results. And essentially, so the telescopes that are coming are, on the one hand, what's called the next generation VLA, the next generation very large array, which is this concept of a telescope that's going to be centered on New Mexico, around the current site of the VLA, near Socorro in New Mexico. Going to have a very dense core of many, many telescopes bunched together that's going to give enormous sensitivity. And then around this, there's going to be a mid array and then these spirals sticking out. And in addition, very long baselines of several thousand kilometers connecting this core to continental scales. Here, there are people in the room that are working on this other telescope, the next generation ngEHT, which is going to combine. So this, by the way, is going to work at frequencies from about 1 to 100 gigahertz. This is going to work at frequencies from 100 about to 300 gigahertz, so higher frequencies. And it's going to combine the existing telescopes in the ngEHT with new ones that are being planned or thought about, and will provide higher coverage of the UV plane. Then there's the BEX telescope, the Black Hole Explorer, that Michael is working on, which will, in addition to the telescopes on the ground, put one single dish on a satellite and to obtain longer baselines. And then there's these SKAs, the square kilometer arrays that are being worked on. To be fair, I'm not completely sure what the current status is, but initially, at least, the plan was to also have thousands of kilometer baselines at even lower frequencies. So all these telescopes really they are all VLBI telescopes. They all are significantly superior to what we had so far, so we can expect that they will bring great improvements. So the ngVLA and SKA, if it includes longer baselines, really is the key point here is going to be sensitivity. It's going to be multiplying sensitivity by a factor of 10. In other words, we're going to be able to see sources that are 10 times weaker. So for instance, in terms of reference frame, how many sources we can see, we had 4,500, whatever, currently. We can expect that to be much, much larger in the future. The ngEHT is going to bring higher frequencies, up to 350 gigahertz. and Bex is going to bring longer baselines. So the combination of all of these, and I think in fact, each one individually is going to be very important, but I'm particularly looking forward to, for instance, combining the three around 100 gigahertz and to reap the fruits of going to 300 gigahertz with the ngEHT and see what we can do in terms of astrometry with this. But I think there's kind of what's the word? An agreement within the community that together these telescopes hold the promise of improving the accuracy of what we can do in terms of astrometry by a factor of 10, from 10 to 1 microarcsecond. And that would enable amazing things, I think. So but the question is, so the science cases that I think are particularly interesting would be to detect and monitor binary black holes, supermassive black holes in the last phases of their orbits. This should enable the detection of the proper motion caused by our motion, the motion of the solar system relative to the cosmic microwave background, which for nearby sources is expected to be about a few microarcseconds per year, so this should be detectable. The science that Don is doing with determining the Hubble constant using masers could also be greatly improved with this, both at 22 gigahertz, but also using water masers at higher frequencies. And one aspect which I think would in fact benefit very strongly from SKA if it were available would be to monitor the orbits of potential pulsars and magnetars around such a star. This would be kind of Einstein's dream, right? To have a clock and orbit around the galactic center, around a black hole. That would be amazing. So these are kind of the effects that I think we could expect to see with these kind of instruments. But in order for that to happen, we will need to work on actually making it happen, particularly on developing new calibration techniques. So there are a bunch of techniques that are being developed here, in particular the frequency phase transfer, where you have receivers at 3 frequencies. The atmosphere is much worse at higher frequencies than on lower frequencies, so you can use the low frequency bands, calibrate the higher frequency bands, and get the both of both worlds. There's another technique that is anticipated to be used at the ngVLA, where instead of having one telescope at each station, you'd have a few, 2 or 3, and one of them will look at your target and the others will look at calibrators. And so you can in real time calibrate phase variations. So all of these are being developed. I think very few have actually been deployed in the field. So I think it's important that in the next 10 years or something, we actually make this happen. But then one of the difficulties we are going to have to face is that calibrators, if you keep looking at them at higher and higher and higher resolution, they will eventually not be point sources, right? Nothing is really a point source. And so as you go to higher and higher frequencies or higher and higher sensitivity and resolution, you're going to see them with more and more structure. So that begs the question, and in addition, turns out if you look at them at different frequencies, you don't see the same position of the sky. So it begs the question of, are we going to be sort of in the situation that Gaia is in already, where everything we're looking at is moving and changing? And so how do we define a reference frame that we use to measure emotions if everything is moving and changing, right? So this is the part that I really worry most about. How, so for instance, going back to here, this cosmological motion due to our own motion relative to the cosmic microwave background, they are at the same level, few microarcsecond for the nearby sources, as the apparent motion due to aberration. So we'll have to be careful, not to repeat this issue that Bradley taught us by looking through his chimney, that you might be looking for the proper motion, but it turns out the aberration is larger, and so you have to be able to separate the two. So these are sort of the questions I think we need to address to actually realize the potential of micro. So in conclusion, VLBI astrometry, I think, is cool. I hope I convinced you that this is true. There's really exciting development to be expected with micro-arc-second accuracy in terms of black hole research. But in order for that to happen, we will have to overcome all of the challenges that are related to, particularly to calibration and getting reference frames that we can actually use to measure positions at the micro-arc-second level. And with it.
Okay, we have at least 5 minutes for questions.
That's great. Do you know I've heard that you can construct a reference frame also from like just boosting to the frame where the CMB appears the most uniform. Do you know if like a reference frame constructed from quasars matches up with that or differs?
Yeah, I don't know. I think that's the idea, right? That if you look at quasars, they are fixed relative to the cosmic microwave background. I'm not sure how you would realize that in practice. I mean, the cosmic microwave background is not something you can use to do astrometry per se. Right? It's a very extended smooth thing. So
Yeah.
You can't measure positions relative to it at the micro-arc-second level.
Yeah.
Yeah.
So yeah, getting to 1 micro-arc-second would be amazing. There's a couple of things you have to overcome. You mentioned some of them. One thing you didn't mention is geodesy. So the positions of the telescopes themselves are moving, and they're moving due to very weird
All
effects,
kinds of things.
right? So there's post-glacial rebound because the glaciers from the ice age are now retreating, and so the Earth is now coming back up, and this can be measured. And telescopes in the US are moving toward telescopes in Europe, which terrifies the Europeans. Only
Rightfully so, right?
What's that? Rightfully so. Yeah, we'll be there in a million years. But I'm trying to get, and also the atmosphere needs to be calibrated out with great precision. Do you think we'll get to 1 micro-arc-second? Like, what are the biggest issues here? And is it just like a global solution? And we'll get so much data that will solve for everything? How does it?
I think we'll get to 1 micro-arc-second locally before we get the globally, obviously.
Right, it's relative to average.
Right. So, and for that, I think the main, because all of these effects that you're mentioning, precisely they are antenna based, right? So each antenna, as you say, is moving for all kinds of reasons. But it's an antenna effect. And so when you do phase transfer, the effect of this is cancelled at the level of how far your calibrator is. So if you manage to densify the grid of calibrators that you can use, and you're lucky enough to have a few within 10 arc seconds or 1 arc minute of your target, then I think you can kind of leverage that against all of these effects that you mentioned. And what worries me most for this is structure. This works well if you have compact sources, but it's not. So again, but again, you could leverage that by having not 1 but several, where each one maybe is doing something different, but on average you can. So I think this is where effort, but we. And especially for ngEHT, for instance, or BEX, we need there's a lot of work to be done, right? Because we need to go from something that looks much worse than this to something that looks like this. So we need a lot of effort, I think, invested in this reference frame business and how to connect the different reference frames. So for instance, frequency phase transfer. If you want to use that to actually gain the astrometry at the higher frequencies, you not only need to be able to transfer the phase, but you need to be able to understand whether the calibrator that you're using at 86 gigahertz is at the same position as the one that you're extrapolating to 355, right? So these kind of shifts in position between frequencies becomes important.
Yeah. Thanks a lot. This is like a really great overview of everything that's possible and happening. And I personally view these like structure effects as more of a like opportunity for astrophysics of agents. But I wonder about this connection between global and local. So do we really need the global reference system at the target frequency to be able to study like proper motions, to be able to study like to observe several sources, tie them astrometrically, several nearby sources, and do this to study like core shifts and everything? Do we really need the global system for that?
Well, yeah, I think we do. So at the zero, so okay, what you're really measuring when you do this, what you're really measuring is the angular offset between the target and the calibrator. This is the quantity that you're measuring. But for instance, in terms of calibration, there are, we tend to forget this, but that when you correlate your data, the VLBI data, at the correlator, there's a whole bunch of corrections that are applied already. Because for instance, we are talking about astrometry at 10 microarc second or 1 microarc second. Yes. The aberration is at the level of 20 arc seconds, right? The aberration correction. The fact that light rays, when they go through the atmosphere, they don't go in straight lines, but they suffer scattering, is also at the level of arc minutes. Right? So you're correcting effects, and you never have to worry about this really when you do astrometry with VLBI, because the correlator takes care of it for you, right? But to do that, the correlator assumes that it knows the position you're looking at. And so if that position is wrong, if you don't have an accurate, then the correction that it applies is wrong by a small amount, but it's a small amount of a large correction. So it becomes important. So yes, I think we need a global information.
Yeah, so the Hubble constant from the extragalactic masers, I guess I didn't realize that it's already so good, because that's the accuracy that most of the methods have. So question for you and Dom.
No.
If all you know are these objects, you may be lucky and may find a few more, but if just with these, can we really beat down the noise further with what we've got or with the upcoming instruments? Because, if you can bring that down to plus minus 1.5, that would be an amaze, because, I think this is the most trustworthy measurement because of the direct, you're avoiding all the distance ladders.
Yeah.
So, so what are the prospects of improving that?
I agree. So I'm going to give you my take, and then I let them. I think one of the issues is peculiar motion, right?
That's why the distant guys are good.
Exactly.
Yeah, you want the really distant ones.
Yeah.
Right. But I think you already have pretty distant. That's pretty good.
Yeah.
Yeah, sure. So it is a combination of statistical uncertainty of with each of the individual distance measures. You can see some of them are not so great compared to some of the others. The peculiar motions are still an effect here. So at a distance of 100 megaparsecs, you have sort of 7,000 kilometers per second recession velocity. A few hundred kilometers per second on that is at the level of the uncertainty in the measurement. So those, I think the best strategy towards improving the maser-based measurement is to try to find more sources.
And more distant.
More distant gets you, like, each individual source contributes more directly to the Hubble constant measurement. But having more sources just mitigates worries about one source sort of tugging things one way or another and being sort of at a higher than you expect peculiar motion or something like this. And we try to handle that, but it's really the error bar is sort of half distance statistical uncertainties and half peculiar motion just not being well constrained at all and difficult to constrain in an absolute sense.
And who is looking for more sources?
Some people.
Some people,
Yeah.
are there enough
Not
people
as many
looking?
as could be. Well, yeah, so there's, we have a couple of proposals going in now for that, bigger surveys. It takes a lot of telescope time to survey a bunch of sources and find the small fraction that hosts sort of good maser systems, but, sub-millimeter, spectral lines are an avenue that I'm hoping will make a dent in this. But the progress has not been as fast as I'd like it to be, because it turns out it's hard to find systems that are bright enough and in the right parts of the sky, somewhat ironically, for the ngEHT, which is the only VLBI array that can do sub-millimeter observations of VLBI, is to actually observe them. So that's been a little bit of a frustration.
I do have a question myself about this.
Please.
So compared to supernovae type 1a,
Yeah.
How far are you going there? The question in
You're seeing the limit right here is about a bit better than 100 megaparsecs there
Yeah.
for the most distant sources. I mean, supernovae 1a are going out to cosmological redshift order.
But
one.
where do they start?
Was it?
Where do they start?
Oh, where do they start? Yeah, so that's fair. They start actually even closer than 100 megaparsec. The most nearby supernovae 1a's are like order 10 megaparsec distances. So they overlap in distance, but of course, in the local universe, supernovae 1a are very rare. These maser systems are very rare generically. And so having a galaxy where they both live in the same one has
Yeah,
yet to
that was
happen.
my question. That
It's a-
whether you.
It's an inevitability if you wait long enough, but
Yeah,
so far we haven't.
But even if they don't,
Definitely able to do it.
even if they don't are in the same, if they are not in the same system, could you use these guys? Because as Raj said, you're skipping the entire
Yeah.
ladder, right? So
Yeah.
could you use these systems to calibrate directly?
Absolutely, that's what they do. So not for the 1As, because there's no galaxy in which they are both there, but for the Cepheus and for other
Yeah,
standard
yeah.
candle-based distance measurements, 4H58's your guy. That one calibrates many of these systems, and it sort of gets you the first rung a little farther out.
Yeah, exactly.
Okay, any more questions? If not, let's thank the speaker again. And yeah, if anyone wants to come for dinner, let me know, and we'll leave around 5:30, 5:45 something.